Today's topic is double integrals in polar form. So far, the double integrals that we have been working with are in Cartesian form, and that's why we had something like this in the last lectures. Double integral of a multivariable function f with x and y as the variables. And then we perform the integration with respect to the differential area, dA, over an integration domain of R, which you can also use D for that, by the way. Well, the fact that we have these two variables, x and y, the fact that we see x and y inside our function, it tells us right away that this double integral is in Cartesian form. And right here you see x and y, you know right away it's Cartesian. And the reason for that is because x and y are like the basis or the foundation of the Cartesian coordinate system. So from now on, you see x and y, definitely Cartesian. Today's double integrals are going to be a little bit different because they are going to be in polar form instead. So in order for us to understand the difference between the Cartesian form and the polar form of the double integrals, it's important that we start by talking about the concept of coordinate systems. So let's take a look here. Two-dimensional coordinate systems. A coordinate system is just a way for us to locate a point in the space. So let's imagine that you have this one object somewhere and you need to find it. Without the direction or location tag of that object, it's impossible for us to go look for it, right? Because we don't know where to go. It's going to be the same thing as point and shape in two-dimensional space. So let's take a look here. Let's put y-axis right here and x-axis. Okay, and let's put a point right here in the middle. Okay, we have this y-axis and x-axis. We have a point right there, and we know it's there, but without further information, we don't know exactly where it is. We don't know the exact location. So one way to put that kind of information is to use the distance in x direction and y direction. And here's how it's done. So we can say that this point is x unit away in x direction horizontally. So right here at x, okay, and this point is also y unit away in y direction vertically. Okay, so with this x and y, we can put a tag to this point, location tag, and that's going to be x and y. And with this, we know the exact location of this point in the space. Okay, this is the origin, by the way. So what we just saw right here is the Cartesian coordinate system, the first one. So let's put a note right here. What we just saw is Cartesian coordinate system. And the fact that the shape that we see right here is a rectangle, right? It means that we use a rectangle to locate this point in the space. And that's why sometimes Cartesian coordinate, we call it a rectangular coordinate. So sometimes we call this rectangular coordinate system because we use rectangle. Okay? Now, it turns out that a rectangle is not the only way to locate a point in the space. We can use other geometric shapes like circle and some other things. Let's try circle first. So what about I use a circle to locate this point? It's going to be something like this. Okay, so we are going to have this part of the circle, a quarter of a circle. And with this circle, this point is right on the circumference, right? And we are going to use the parameters of this circle to locate this point. So first of all, I'm going to say that this point is r unit away, which is the radius of this circle. So let me put this r unit away. Okay, that is the radius. So there you go, we have this one, the first parameter for this point in terms of circle. But r is not enough because all these points on the circumference of this circle is r away from the origin. we need more information, and that would be the angle that this path, the path that we just drew, makes with the x-axis. Okay, so this path makes theta with the x-axis. So with these two parameters, r and theta, we know the exact location of this point in the space and on this circle. So another way to look at this point is going to be this r and theta. Okay, and what we just saw right here is the polar coordinate. So let's make a note right here. This is polar coordinate system, and the reason for that is because we use the circle to locate a point in the space. Circle. All right. Well, to me, Cartesian coordinate is more intuitive because usually we have x and y axis on the graph anyway. So using x and y values to locate a point makes more sense. But sometimes you might run into a situation that you have to work with problems that has object with circular shape. In that case, polar coordinate is going to be more convenient to use. So you can make a note here that Cartesian, we mostly see Cartesian coordinate system, so it's for general use. Okay, and polar coordinate is for problem with object that has circular shape. So for object with circular shape, okay, let me change this. Put this on the same line. Now the question is, can we, since both of them are just a way to locate points in the space, right? Same point, but different system. Can we switch around between them? And the answer is yes. For example here, if you have a coordinate in polar coordinates, like r and theta, can you transition from this r theta to x and y? The question is this. Can we do this? Change r theta to x and y. So let's try to make this happen. First of all, we are going to use trigonometry to find this relationship. So let's take a look here. Let's take a look at this triangle. I'm going to highlight this triangle right here. Okay. This one. All right. So from this triangle, I want to find this cosine of theta. So let's find it. Cosine of theta is going to be equal to the closed side divided by the hypotenuse. The closed side is this down here, which is x, right? And hypotenuse right here is r. So you can you know right away this cosine theta equal to x over r, which means that x is going to be equal to r cosine theta. And there you go. We have this first relationship between them. Okay? If you know r and theta, you can find x by using this relationship. Now let's take a look at another one, trigonometry again. So we have this sine theta right here. So I want to look at this sine theta, and it's going to be the opposite side, which is this, divided by the hypotenuse. The opposite side of this is going to be y. By the way, this closed side is going to be x. So sine theta is going to be equal to y over r. And if you switch things around, you can get this y equal to r sine theta. And there you go, the second relationship, y equal to r sine theta. So if you know r and theta, like this, you know r and theta, you can find y by using this. So there you go. If you know this r and theta, you can find x and y, no problem. So you can transition from r theta to x and y without any problem. The question is, can we do the opposite? Can we go back from x and y to r and theta? So let's try to make this happen again. To go back from xy to r theta, I am going to use something different. Here I'm going to use Pythagoras. So let's take a look at this same triangle again. I have this relationship, x squared plus y squared equal to r squared, right? Pythagoras. And with this, I can move things around and I get this relationship. R equal to square root of x squared plus y squared. And there you go. Third relationship in the opposite direction. If you know x and y, you can find r. If you know x and y like this, you can find the first one, r. Now for the last one, I am going to use the trigonometry again. And this time it's going to be tan theta. So tan theta is going to be close divided by opposite side. Close is going to be x divided by y. So, oh, I'm sorry, it's going to be opposite over the close side. So it's going to be y over x. Sorry about that. So with this, I can find theta equal to arctan of y over x. So there you go, the last one. If you know y and know x, then you can find theta. So there you go. With x and y, you can find r and theta. This is the opposite relationship. So there you go. We have these four relations between these two coordinate systems. So keep this in mind. We are going to use this quite often in this topic. Okay. Now, we can go back and forth between r theta and x and y. What about the double integrals in Cartesian form and the polar form? Can we switch them around? So let's take a look here. I am going to start with the double integrals in Cartesian form. So it's going to be down here. Double integral. Okay, in Cartesian form, definitely is going to be function with x and y in it. Cartesian. And then we perform the integration with respect to differential area over an integration domain R. Alright, we see x and y here, we know it's Cartesian. Right, you can make a note right here, Cartesian. And by now, let's talk about this dA first. At this point, we know that this dA represents the area of a tiny rectangular piece in the integration domain R. Alright, so make a note right here that this dA is the area of small rectangular piece. Piece in, okay, let me put it right here, piece in integration domain R. How does that look? Let's take a look here. So let's assume that we have this y-axis and x-axis, and let's build an integration domain R that is simple. So we are going to use constants for all the boundaries. So I'm going to put this constant of A right here, constant of B. Okay, what about I use blue instead? Okay, that is A, and this one is B. And another constant, the lower boundary is at C, and the top one is at D. Okay, so there you go, we have this integration domain R, looking like this. And then I want to put a mesh over this. Put small step in x direction. Okay. Something like this. Okay. Small steps in x direction. And small steps in y direction. There you go. And I'm going to take just one piece out of that, this mesh. This one piece right here, and I am going to magnify it. Okay. Okay, so it's going to look something like this. Alright, so same color. It's going to be this piece right here. And the area of this piece is dA. Just a small piece in the integration domain. So you are looking at this piece and the area is dA. And in order to find the area of this, of course we can use the length of each side of this rectangle. This one is dx, right? And this is dy. So as you know, dA is equal to dx dy, or also equal to dy dx. And that's why in the last lectures we have to decide whether it's dx dy or dy dx. And this is based on the shape of this rectangular piece from this right here. Now we want to transition from the Cartesian form to polar form. So let's do something right here. So from now on we are going to move to this double integral of a function in polar coordinate. So we can no longer use a function with x and y. We are going to use r and theta instead, which is the main variables in polar coordinate. Right, r and theta. So it's going to be this r and theta first step. You see this, you know right away. This is polar form. Now, we are going to perform the double integral over with respect to the differential area again. So this dA is going to come back right here, dA, and it's going to be over this integration domain of r. So let's make a note once again that this dA is going to be the same area of small piece, which we don't know whether it's rectangular or not, in R. Okay? And let's make a note here, it's going to be non-rectangular. And we are going to see soon why it's non-rectangular. So I'm going to do the same thing over here. I'm going to start with the integration domain that is simple to visualize. Okay? So we are looking at two values here. Constant value of radius and constant value of angle. So first of all, constant value of the radius is going to be something like this. Constant value, first one. I'm going to call it A. Constant value of radius, number 2, right here. Okay, let's make it a little bit bigger. So, something like this. Alright, constant value of radius, number 2, B. And now constant value of theta, angle that makes to the x-axis, constant. Another one. Okay, I'm going to call this one alpha. Okay? And another one like this. And it's going to be beta this time. And as you can see here, we start to see the shape of this integration domain. Sort of like a pizza, a slice of pizza that you already take a bite on it. Okay? So it's going to be this. Okay? And now we are going to do the same thing, put small steps in both directions. For the angle, it's going to be this. Okay? And for the radius, it's going to be this. Okay, and I'm going to take one piece out. And I'm going to magnify it again. Alright? Okay, and I should get something like this. Okay, x-axis. Smaller version of what I had before. So it's going to be something like this. Small size of what I had before. Except that this time it's very small. Okay, I should put blue over here. Very small piece, but this time we magnify it. It's going to be something like this. And the area of this should represent the dA of this double integral in polar form. Okay, this one. All right. So this area of this is going to be dA. And what we know so far is that the step on the radius direction is going to be dr. Alright, and the step in the angle direction is going to be d theta. But as you can see here, this shape is non-rectangular, which means that this dA is not going to be equal to dr d theta, which means that this dA, we can't use this. We cannot use this. Cannot use this. So we have to use something else. So we are going to find out about this dA in the next slide. What should it be? Alright. So on this slide we are going to find out about this dA. Okay, so our main goal is this, and this is going to be the area of small piece. We want to find the area of that piece. Okay. But first of all, let's start with something simple. So let's start right here. So we have this, okay, y and x axis, and we are going to have this circle on this graph. Okay, let's build a circle like this. Okay, and then we want to find an area of this piece. Okay, and just this one right here, let me highlight this. It's going to be this piece that we want to find the area, and this piece is a part of the circle with radius r. So we know the radius of this piece, and we know this theta right here. If you know these two variables, parameters, can you find the area of this? Okay, area of this. So let me give you this formula. The area of this is going to be equal to 1/2 theta r squared. So let's put a box around this. 1/2 theta r squared. So if you know the angle, if you know the radius, you can find the area of this. Okay. By the way, let me change this to easier to see. So let's try this out. What about I want to find the area of the whole circle? That is when theta equal to 2 pi, right? So that is the whole circle. Okay, so what do we get here? Area is going to be equal to 1/2 2 pi r squared. And in the end, we have this pi r squared. And this is the popular formula for the area of a circle. Area of circle. Okay, now we are going to make use of this formula to find the dA, the area of the small piece. So let's take a look right here. So once again, we have this small piece. Okay, and it should look something like this. Let's magnify it. The small piece. Okay, and something like this. Okay, this is the reference point, and I'm going to build this one. Okay, and this. Okay, the area of this is going to be dA. Okay, now I want to find the area of this, and I want to make use of this formula. So I'm going to do that by putting information to this piece. Let's assume that this point right here is when the radius is equal to r1, and this point right here is when the radius is equal to r2. From the look of this, you know right away that this r2 has to be greater than r1. Okay, so first of all, I am going to find the area of the whole piece right here. this whole piece. All right, and it's going to be the same, quite similar to the one that we found right here, a slice of pizza. Okay, this one, you want to find the area of this. Okay, give me some time. It's kind of hard to draw the whole one right here. So it's going to be this 1 over 2. So for this one, it's going to be 1 over 2 and theta right here. Let's put a theta down here. Oh, by the way, let's put delta theta instead. So let's use delta theta, the change in theta. So this is going to be 1 over 2 times theta, which is delta theta right here. And for this one, big piece is going to be r2 squared. All right? And now I want to find this smaller one, the area of this smaller piece, this one. Okay? And this one is going to be quite the same. 1 over 2, same angle, delta theta. But this time the radius is going to be r1. So this is r1 squared. And when I find the difference between these two areas, it's going to represent this one. Okay? So I am going to find the difference between these two pieces, and it's going to give me this area of the dA. Okay, so I'm going to have this minus, and in the end this is going to be equal to well, what about I put just a for now. Okay, let's just put a for now, and it's going to be this a equal to this right here. Okay, let's work on this these two terms. I am going to have this 1 over 2 common terms right here in the front, 1 over 2, and then inside I have this r2 squared minus r1 squared, and I take the common term delta theta out to the right hand side, delta theta. Okay, now I'm going to do some factorization. It's going to be 1 over 2 r2 plus r1. Okay, nothing fancy, right? Front square minus back square, you get front plus back times front minus back, and this is delta theta. Okay, now this term r2 minus r1, it's going to be change of r, which is delta r. Alright, and now let's take a look at this one. 1 over 2 times r2 and r1, this is going to be the average value of r. Average. So you can make a note right here that this one is going to be average value of r. What is that? It's going to be right in the middle of r1 and r2. It's going to be this. This one is going to be r right here. Happens when the radius is right in the middle. Okay? So this should represent r right here. It's going to be, we are going to use r for that. So in the end, we are going to get this equal to r, which is the average of the r2 and r1, times delta r times delta theta, and that's equal to a. Okay, and now we want to make this piece very, very small. So this a is going to become differential area. So this, make it small. So what's going to happen? This is going to become differential area. R stays the same, just very small r. This delta r is going to become dr. And this delta theta is going to become d theta. And there you go, we have this. Differential area dA for a double integral in polar form has to be equal to r dr d theta. You know, I can just give you this expression from the beginning, but I want you to know where it comes from, and also want to show you that this r right here just doesn't come out of nowhere. There is a reason behind it, and you just saw it. And let's take a look here. Since there is a product between this delta r and delta theta, it means that we can switch their places, right? Even though I switch the places, it doesn't affect the formula. It's still the same area, which means that this dA is also equal to r d theta first and then dr. Same thing. But most of the time you are going to run into this order. You are going to integrate with respect to r first. But if you run into this one, don't be surprised. It can be done too. Alright, now let's take a look at the double integrals in polar form, and we have two variations for that. So I'm going to split the screen right in the middle, right here. Okay, and okay, let me change that, not so middle, maybe around here. Okay, and this is going to be the first variation of the double integral in polar form, and this is the second one. Now let's take a look at the first one. Of course, it has to be double integral of a multivariable function, but this has to be in terms of the r and theta, the variables for the polar coordinate. Okay, and since we know that this dA is equal to r d theta, we can safely put it here. r d theta. There you go. And that is the first form, and let's talk about the integration domain. Let's make it simple this time. I am going to make all these values r and theta constants. So r is going to start at a constant value of a and ends at a constant value of b. Okay, and I want to have more space right here. So let's put the second integration sign right here. And for the angle, theta is going to be constant as well. Start at the constant value of alpha and ends at a constant value of beta. Alright, now as you can see here, all the radius and the theta are constants. It means that the boundaries for this integration domain are going to be constant. So make a note right here that all boundaries are constant. All bounds are constant. Okay. That is the first form, and I'm going to put a box around this double integral. Okay. Alright, now let's take a look at the integration domain of this case. So I'm going to draw a graph down here. Okay, y-axis and x-axis down here. Now let's take a look at the boundaries. R constant at a, let's start with this one. Constant at a, let me do this. Maybe something like this. Radius of a, constant. Alright, now next one is going to be constant radius of b, and it's going to be something like this. Okay. Okay, let's assume that this is constant of b. Now for the angle theta, let's take a look here. Theta equal to alpha, and it's going to be constant. So let's assume that this is angle of theta. So make a note right here that this one right here is alpha right here. Okay, and the angle ends at theta equal to beta. It's going to be this. Alright, constant, and okay, we run out of place, so I'm going to make an arrow right here. Goes to the end, and this one is beta. Alright, and this one, let me fix this. Supposed to be alpha. Okay, with all these boundaries, you can see the integration domain trapped between them, and it's going to be this. Okay, constant radius, constant angle, and constant radius. Okay. Okay, like this. This is better. Now let's take a look here. We are going to integrate this with respect to r first. So this is going to happen at theta equal to alpha. Right here, we are going to sweep between the two curves of r. So it's going to be this sweeping pattern, like this arrow. And as you can see here, we sweep between two curves again, just like before. The same rule that we had, we sweep between two curves first. So here we are going to start at the inner curve. So you can consider this as the inner curve and this one as the outer curve. Alright, so let's make a note right here that this r equal to a is the inner curve. Inner curve, and this one r equal to b is outer curve. Alright, now that we sweep the radius already, we can sweep the angle, this one d theta, and we are going to repeat this pattern again and again until we cover the whole region of this integration domain. Okay, and this one, since we have everything all constant, it's going to be equivalent to the Fubini's theorem number 1 for the double integrals in Cartesian form. So you can make a note right here that this is equivalent to Fubini's number 1. Okay, now let's take a look at the second variation of the double integral in polar form. Once again, it's going to be double integral. Okay, and once again, same function of r and theta. And dA, of course, it's equal to r d theta. Okay, d theta. Okay, now for this variation, it's going to be a little bit more complicated. Instead of having a constant r, we are going to have radius that is variable. The value of the radius is going to change along the integration. So let's take a look here. Instead of having radius as a constant value of a, it's going to change depending on theta. Alright, so r is going to change depending on theta, and we are going to use this function g1 of theta instead. So same thing as the outer curve, r right here is going to change according to the theta, and we are going to define it as g2 theta. So this one is going to be r equal to g2 theta. So once again, this is inner curve, and this one is outer curve. And for the angle, it turns out to be same constant. So for the theta is going to be equal to alpha, just the same, and this one is going to be equal to beta, just like in the first variation. So you can make a box around this one as the second variation of the double integral in polar form. So this one, alright, and it's supposed to be the harder one, right? Because the r is more complex this time. So you can make a note right here that the inner and outer, okay, make a note right here that inner and outer are not constant. Okay, not constant. You can say that outer radii. What about radius right here? So let me change this to inner and outer radii. Okay, are not constant. So keywords is right here, not constant. So how is it going to look like? Let's take a look at this graph. So once again, we have this y-axis and x-axis. Okay, let's start with the easier ones. So angle is still constant, alpha and beta. So same thing. So we are going to get this angle of alpha, this one, right here, alpha. And then another one, constant, at beta. Something like this, just like the same. This one, larger angle, and this is beta. Okay, but now for the radius is going to be not constant. This is going to change depending on the value of theta, which means that the radius can change like this. It doesn't have to be circular, okay? Depending on the angle that you are in. for the outer one, for the G2, this one can change with respect to theta. So it may look something like this. At different theta, we have different radius. So in the end, we have this kind of shape for the integration domain. Angle, constant, but for the inner curve, it's going to be non-circular, non-constant, not constant. For this one, all right, what about I make it a little bit more obvious? So let me change this. Okay, maybe something like this. Okay, this looks better. Oh, what happened? Let me try again. Okay, so the outer one is going to be this kind of shape. All right, so you can make a note here that this for this one is going to be circular inner and outer curve. Circular, circular, inner and outer curve. Circular means that r is constant, r constant. For this one, it's going to be non-circular, non-circular, inner and outer curve. Okay, so we have these boundaries. So let's take a look here. We are going to integrate with respect to r first. So we are going to sweep from G1 theta to G2 theta, and it's going to look something like this. Sweep from the inner curve to the outer curve. So we have this sweeping pattern, right? Oh, by the way, this inner curve right here, let's highlight this as G1 theta. And as you can see, it's not constant. Same thing here. Radius not constant, and I'm going to name this G2 theta. All right. And once you are done with the integration with respect to r, you are going to sweep the theta, and it's going to create this, replicate this sweeping pattern all the way through. Okay. Until you reach the end of this region, the whole domain region. So there you go. We have covered the whole r. And this one is equivalent to the Fubini's theorem number 2. Equivalent to Fubini's number 2. And the reason for that is because of this function right here. Right, G1 theta and G2 theta. Now that you have seen these two variations of the double integrals in polar form, we are ready to move to the examples. So let's work on this example number 1 right here. Here we are supposed to find the double integral of a multivariable function x and y. And when you see something like this x and y inside your function, you know right away that this double integral is in Cartesian form. So x and y, you know right away it's Cartesian. And we are supposed to perform the integration over a domain region. It's going to be r right here, which is bounded by these lines and curves. So let's take a look at them. First one is going to be x squared plus y squared equal to 1. Definitely a circle of radius 1. Next is x equal to y, just a straight line, and last one is y-axis, which is equivalent to x equal to 0. Same thing. I'm going to start by drawing this domain region on a graph. I want to take a look at the shape of this r. So let's do this right here on the left hand side. I'm going to put y-axis right here. Okay, and x-axis. Let me extend this a little bit further. Okay, so I'm going to start with the first curve. X squared plus y squared equal to 1. A circle of radius 1. Okay, let me put y right here and x right here. Circle of radius 1. So this is 1 and 1 right here, and around here. Supposed to look something like this. Okay, circle of radius 1. So this is 1 and minus 1. Okay, next line is x equal to y. Easy. One straight line. Okay. Now last one is y-axis, which is already there. So I'm going to highlight all these lines so that we can see the domain region trapped between these three lines. So it's going to be this, x equal to y, right here. Okay, and next one, y-axis. And the last curve is going to be the circle of radius 1. I'm going to take just one part of that, which is right here, the outer boundary of this region. So this is going to be the domain region of this double integral. Okay, this R right here. And from the observation, oh, by the way, the shape of this is like a piece of pizza, right? A slice of a circle. So from the observation, I can see that this shape is circular, part of the circle. So we are looking at a circular shape. Circular, even though it's not a circle, it's related to a circle. Circular shape. And when you see something like this, I told you that polar coordinate is suitable to solve a problem like this. So we are going to try to solve this double integral using polar form. So we are going to try to solve this using polar form instead of Cartesian, which is given to us. Polar form to solve this. Okay, and this is based on the circular shape of R. Okay, so polar form of the double integral should look something like this. So it's going to be this double integral of a function, and function has to be in terms of r and theta, because polar form, it has to be in terms of radius and angle. So this function right here is supposed to be r and theta, and by now we know that dA is supposed to be r d theta. And we also need to work on these boundaries, like r right here equal to something which we don't know yet, and this one equal to something, theta equal to something, and also here, all the boundaries. At this point, we don't know any of these yet. Okay, so let's take a look at what we have right here. We have this multivariable function in terms of x and y. It's in Cartesian form, so we have this f of xy right here. F of xy. Not minus. Let me change this. Function of x and y right here is given to us equal to x and y. But we need this. We need a function in terms of r and theta. So we have to do something with this function, x and y, to make it r and theta. So we are going to transform this into polar form. So let's do this. We are going to transform this multivariable function in Cartesian to polar. So make it polar. So first of all, let me put this function of r and theta is what we want. Okay, let me put a boundary right here. Okay, this is what we want. Okay, so I'm going to use the relationship that we built in the first slide. It's going to be this. We have talked about this. If you forgot, you can go back and look at this. X equal to r cosine theta. Relation between Cartesian and polar. First one, x equal to r cosine theta. Second one is r sine theta equal to y. Third one is the Pythagoras, x squared plus y squared equal to r squared. But let's stick with these two for now. So I know that x equal to these and y equal to, well, this term. I can put them into here. X equal to r cosine theta. I am going to get this. R cosine theta for x, and then y equal to r sine theta right here. So this is going to be y, which is equal to r sine theta. So there you go. Everything is now in terms of r and theta, and we can get this right here equal to r squared sine theta cosine theta, and that is the function in terms of r and theta, radius and the angle. So there you go. We have this function for our double integral in polar form. And of course, dA is equal to r dr d theta. We have talked about this in the last slide, so I'm not going to repeat that again. What about I change this to dA for now? Okay, let's make this dA. And let's put everything that we know so far into this, this double integral. So it's going to be equal to this double integral. Okay, let me work right here. Double integral of a multivariable function of with respect to r and theta, in terms of r and theta. So it's going to be this right here that we just found. So it's going to be this r squared sine theta, all right, cosine theta. Okay, I don't like the space. I'm sorry about that. Let me work on this again right here, equal to double integral of the function of r squared sine theta cosine theta. And for dA right here is going to be equal to r dr d theta right here. R dr d theta. So you can make a note that this one is function of r and theta, and this one is dA. Now for the boundaries, let's take a look here. Inside the inner radius and the outer radius, let's start with this. So let's take a look at this piece on the left hand side. The inner radius is right here, right at the origin, and it's constant all the way through. So this is going to be a constant of 0. Radius is 0 at this point, at this origin. So we can put r equal to 0. Now we can take a look at the outer radius. Outer radius is going to be this line on this circle of radius 1. And as you can see, on the circle of radius 1, of course, this r has to be 1. So the outer radius of this double integral is going to be a constant of 1. So we create this sweeping pattern from 0 to, let me use, oh, I'm sorry, what happened? Oh, okay. So we are going to create this sweeping pattern from the inner radius to the outer radius, something like this arrow. Okay? Now let's work on the theta. Theta is going to be, starting point of this theta is the, right here. Let's take a look right here. This theta, since we are looking at this line x and equal to y, we know this is going to be equal to 45 degrees, which is pi over 4. This is supposed to be pi over 4. So the starting point of the angle is going to be pi over 4. Ends at y-axis. So you know at y-axis, go all the way through, it's going to be pi over 2. Okay, the last angle of this sweeping is going to be theta equal to pi over 2. So there you go. We got everything that we need for the function, for the differential area, and for the boundaries. So why don't I, okay, it's fine. Okay, once again we are going to create this sweeping pattern again and again until we cover the whole region. So now we just need to work on this double integral. Okay, so we are going to start working from the inside and then move to the outside. So let's do it right here. It's going to be equal to the double integral of r equal to, starting point, inner radius 0 and outer radius equal to 1. Angles start at 45 degree, pi over 4, and ends on the y-axis, theta equal to pi over 2. Combining all these terms, I have, okay, r squared right here and r right here, it combines to r cubed. So I have this r cubed, and we have this sine theta, cosine theta, dr d theta, and we are going to perform the integration with respect to r first. So starting from the inside, okay, inside integration with respect to r. Once again, this is integration with respect to r. What about I put it right here? integrate with respect to r, which means that we are going to treat theta as a constant. Okay, treat theta as constant during the first integration. So let's do that. So integrate r cubed right here with respect to r. It's going to be r to the fourth divided by 4. So this is what you got, r to the fourth divided by 4. Okay, and everything else stays the same. Sine theta, cosine theta, and you are supposed to evaluate this at two values of r, 0 and 1. So this has to be evaluated two values, r equal to 0 and r equal to 1. Okay, and this is d theta. You need to integrate again with respect to theta, starting from pi over 4. Oh, I guess from now on I can just put pi over 4. You should already know that this is supposed to be theta, right? 2 pi over 2. So let's try something right here. 1 goes in, it's going to be 1 over 4. What about I take this 1 over 4 out? This is constant, right? I'm going to get it out right here. 1 over 4. This is easier. Okay, so 1 goes in, I get this r to the 1 to the 4th, which is 1. So sine theta. So 1 goes in, I get this sine theta, cosine theta. Minus 0 goes in. Now 0 goes in, here everything goes to 0. Okay, this is convenient. So the back term is going to be 0 because of this r equal to 0. So let's continue with that. So in the end, I have this at this step 1 over 4 outside. I still have this double 1 integral from theta equal to pi over 4 to theta to pi over 2. Inside I have this sine theta coming from this, right? It's just sine theta and cosine theta. We need to integrate this with respect to theta. At this point it's just cal 1, right? One variable to integrate. But you see two locations of theta inside this function, so you have to think carefully when trying to solve this. So you can use substitution to solve this. So you have some choices here. So you can use substitution, right? For this one, number 1, you can use substitution, okay? Or you can use trigonometry identity. If you can simplify this, it might be faster. Okay, either use sub or trig. Okay, so what about I'm gonna try to use trigonometry properties first. When I see something like this, this reminds me of this property right here. Sine 2 theta equal to 2 sine theta cosine theta, which means that this term right here is going to be equal to sine 2 theta over 2. Okay, let me try that. So this is going to be equal to 1 over 4, same integration from pi over 4 to pi over 2. And this has become sine 2 theta over 2 d theta. Okay, and what about I change this? I get rid of this 2 and move it outside. This becomes 8. Okay, this becomes 8, and all I need to do now is to integrate this sine 2 theta with respect to theta, and this should be easy. Okay, so this is supposed to be equal to minus cosine 2 theta over 2 when I integrate this. So equal to minus cosine 2 theta over 2. Okay, integrate sine, you get minus cosine, and 2 right here comes from the inverse chain rule. So you are supposed to evaluate this at two value of theta, pi over 2 and pi over 4 down here, and pi over 2, and we still have this 1 over 8 right here. And since we have this 2, I am going to take it outside, okay, to be 16. 1 over 16, and I'm going to take the minus sign outside too. Minus right here, better. Okay, so in the end I have this equal to minus 1 over 16. Pi over 2 goes in, I get this cosine of pi. Minus cosine of pi over 4 times 2, I have this pi over 2. So this is going to be equal to minus 1 over 16 cosine of pi minus 1 cosine of pi over 2, that's 0. So in the end I have this 1 over 16 as the answer for this problem. So there you go. I recommend that you try trigonometry property. It can make things a lot easier for all of us. Okay, so pay attention to this right here, trigonometry trick. Okay, let's move to example number 2. Once again, we are going to work on something with x and y. So you see x right here and xy right here, you know right away this is Cartesian. And this is about volume. Okay, volume of this z equal to x squared over x squared plus y squared. So this is going to be the top surface of this volume. Okay, so we know about the top surface. Okay, and xy plane, and we have this as the base. So the information for the base is right here. A circle of radius 3 and a circle of radius 4. So this is R, or the base, which means that this is definitely double integral problem. Okay, once again, I am going to start by looking at the shape of the integration domain in the space. So let me draw this on the graph once again. Okay, so this is supposed to be something like this. Okay, this is good enough. Y-axis and x-axis. Okay, let's take a look at the curves that we have. So first of all, it's going to be a circle of radius square root of 3. Okay, maybe somewhere around here. So let me make one circle right here. Square root of 3. First one. Okay, doesn't look good. Let me fix that. A little bit better. Okay, so that is the first curve. Now let's take a look at the second curve. We have once again a circle of radius 2. Okay, 2 squared, that's equal to 4. So I have this one around here, radius of 2, radius of 2, and radius of 2 once again. So combining all of this and down here. So there you go. The base is supposed to be between these two circles. So we are looking at this as the integration domain. So what you see right here, shaded area here is the R. And once again, this is circular shape. From the observation, this is circular shape. Well, you can say that circular R. Shape of R. And I'm going to do the same. Tripolar form. Okay, I need this. Everything again. Double integration, double integral of a multi-variable function f. Once again, I need r and theta, and it's going to be with respect to differential area. Okay, and I need to define this r right here, inner curve, inner radius equal to what, outer radius equal to what, theta equal to what, and the starting of the theta and the end of theta, all these terms. Okay, I need all of these in order to complete this, but everything that is given to us is in x and y, so we have to do the transformation again. So let's take a look here. Z equal to x squared divided by x squared plus y squared. That is the function that we have. So we have this function in terms of x and y equal to x squared over x squared plus y squared. And we cannot use this because we need this function in terms of r and theta. And once again, we are going to rely on the relationship between polar and Cartesian, this one. X equal to r cosine theta, same as example number 1. Y equal to r sine theta. Okay, just these two, and we are going to transform this. Oh, not just these two, we need this too. X squared plus y squared equal to r squared. That is the third relationship, okay, using Pythagoras. So this right here is going to be, we need this function in terms of radius and theta, starting with the first one. X right here, x squared. X equal to r cosine theta, which means that x squared is going to be, well, let's put this, r cosine theta square. Alright, divided by x squared plus y squared, and we are going to use this relationship, the third one, x squared plus y squared equal to r squared. Okay, once again, let me put this right here. So it's going to be a little bit easier than last time. This one is going to be r squared cosine theta squared over r squared, so we get some cancellation. So this is going to go away, right? So in the end, we have this function in terms of r and theta equal to just cosine theta squared, and that's it. So we have this multivariable function in terms of r and theta ready to be used. Okay, so with this, we can complete this double integral in polar form. Once again, double integral. Function is cosine theta squared, and dA, you know it's r dr d theta. Okay, so now let's talk about the inner radius. So this one is inner radius, and here, right here is the upper. Okay, so let me write it right here, inner radius. So I'm going to start with the inner one, equal to what? So as you can see in this area, the inner radius is going to be this, inner radius of this region. Okay, right here, and as you can see, this radius is square root of 3, and it's constant all the way through, right? Inner radius constant, square root of 3. So we can put this square root of 3 right here. What about outer radius? Of course, it has to be this, starting from right here. Okay, constant of 2 all the way, and comes back to the original point. So this is a constant radius of 2. Now what about the angle? Angle starts at, of course, right here. I'm going to use right here as the starting point, starting from 0. Theta start at 0, and it goes all the way through 0 to pi over 2, to pi, and then 3 pi over 2, and then to 2 pi. So it starts at 0 and ends at 2 pi. So there you go. We have the range for the angle from 0 to 2 pi. Okay, so everything is ready. So let's work on this double integral right here. Let's put everything right here, double integral. So I'm going to put cosine to theta squared, r dr d theta. Okay, and r start at constant value of square root 3, ends at r equal to 2, theta at 0, start at 0 and ends at 2 pi. And once again, same thing as example number 1, we are going to work from the inside to outside. So we are going to integrate with respect to r first. With respect to r first. And we treat theta as constant. So as you can see here, we have this one r right here. So it's going to be equal to r squared over 2. Okay, r squared over 2. And cosine theta squared stays the same. Okay, let me move things around a little bit. So this is going to be r squared over 2 cosine theta squared stays the same. Alright, and we are supposed to have this, evaluate this at two values of r equal to 0 and r equal to 2. And once again, integrate again with respect to theta. At this point, I just put 0 and 2 pi here. It's obvious that these two values are for the theta. Okay, now this 2 right here is a constant. I'm going to take it out outside the integration. Right here, 1 over 2 is going to show up right there. Okay. Oh, by the way, I make a mistake. This is supposed to be r equal to square root of 3. Okay, right here, square root of 3. So, let me work on this. 2 goes in right here. It becomes 4. Cosine theta squared minus square root of 3 goes in. Right here, it's going to be 3. Cosine 2 theta. So this is going to be equal to cosine theta squared. Right, 4 minus 3. So let's continue your calculation right here. So this is going to be equal to 1 over 2 integrate of 0 to 2 pi for theta, the range of theta, and we have this cosine theta squared again right here. So we are supposed to integrate this cosine theta squared with respect to theta. This is once again Cal 1 stuff. And as you can see, integrate cosine theta is easy, but integrate cosine theta squared, not so simple, right? So you can choose methods to work on this. You can try substitution, all right? You can try by parts if you want to, or you can try some trigonometry property. Maybe it can make this a little bit easier to work with. I don't like trigonometry, a function like this with the square. It's sort of hard to deal with it, so I'm gonna try to make this square goes away. So I think about this relationship between cosine 2 theta and cosine theta squared, and it goes like this: cosine theta squared equal to 1 plus cosine 2 theta over 2. So I don't like this kind of term in my integration, so I prefer something like this. So I'm going to put this back into the integration. So 1 over 2 stays the same, and 0, 2 pi's the same. So instead of cosine theta squared, I am going to use this 1 plus cosine 2 theta over 2 d theta. And since I have a constant like this, I am going to take it outside, combine it with this. It's going to be 4 right here. So right now I need to integrate this with respect to theta. Okay, so equal to 1 over 4 stays the same. And 1 right here, integrate this with respect to theta, I get theta. Integrate this with respect to theta, integrate cosine, I get sine. Plus sine 2 theta with over 2 right here from the reverse chain rule. So I'm supposed to evaluate this at two values of theta, 0 and 2 pi. So as you can see here, when you use the right property, it makes life much easier. Okay, if you try by part, it's going to be long, much longer than this. So this is going to be equal to 1 over 4. First term goes in, 2 pi goes in here and goes in here. So I get this 2 pi. Okay, 2 pi goes in, 2 pi right here. Sine 2 pi times 2 is going to be sine of 4 pi over 2. Okay, and I'm supposed to minus with 0 goes in, 0 right here and 0 right here. It's going to be 0 plus sine 0. Okay, so sine 0. Okay, and we all know that this is 0, 0, and this 0. So in the end, we have this 2 pi over 4, which is equal to pi over 2 for the answer of this example. Okay, and since this is about volume, so you can say that this is unit cube. The volume is this cubic unit, pi over 2.